graph is a straight line, you can recover the slope very easily. The slope of a linear function is just that parameter m. And maybe the last remark worth making is if you happen to know the slope of a linear function, the slope of a line, and you know a point that it goes through, then you can write down an equation for that line, not in the format of a linear function, but almost as one, in point slope form. If you know some point that's on a line, and you know the slope, then you can write down an equation for the line. Does that look like an equation that you could solve to get something of the form y is equal to mx plus some stuff? Yeah, of course. So there's a short recap of last time. And kind of the philosophy here is if you know this fact about a line and that fact about a line, then you can recover the line. In general, if you know any two facts, then with maybe some creativity, you can figure out completely what that line is. And here's one example of such things that you might know. Let's talk about just two more words, then we'll be done with last time's notes. The words are parallel and perpendicular. And in order to motivate some of this stuff, maybe I'll start by just drawing two lines that appear to be more or less parallel. You might say that, well, up close those don't really look parallel, but they don't even really look like lines. You get what I was trying to draw. Take a look at those two lines, maybe even the ones that you drew, because you probably drew better parallel lines than I did. How do their slopes compare? And that seems intuitively correct, right? If two lines have the exact same slope, they're either the exact same line or they'll never cross. So here is a fact. If I give you two lines, y equal to mx plus b, and y equal to, oh, yep, I zoomed in too close. Y equals mx plus b and y equals nx plus d. Thank you. And they're parallel. Well, then what do you know? You know that they should have the same slope. So m should be equal to n. So one fact that you might be told about a line is you might be told that it's parallel to another line. If you know that fact and one other fact, you should be able to figure out that line entirely. So let's do an example of that. Let's suppose I tell you that a line goes through the point 1, 1, and is parallel to the line y equals 3/2 x plus 4. Is that enough information to figure out this new line? Yeah. What's its slope? 3/2. Slope should be 3/2. Do I know a point on this line? Yeah. So I can write something in point slope form and solve. Point slope form. So I know that y minus the y value, 1, is equal to 3/2 times the x value, the x minus the x value, which is 1. That look like you could solve it for y and get something of the form y equals mx plus b? Yeah. Yeah.
Does it have to be changed into y equals mx plus b, or can you leave it in one slope?
Well, so let's see if I can. So this prompt, as written, is sufficiently vague that, yeah. That would indeed satisfy the prompt. If I were to instead ask for a linear function whose graph is this line, then you better get it all the way down to a linear function. So the answer to your question is make sure to read the prompt carefully. The prompt as written, point slope formula, is indeed an equation that gives that line. Yeah. Any other questions? Yeah.
Would it be minus a half? I don't know if I did it wrong, but
I think it is minus a half.
make sure I did it
People agree that it's minus a half?
Yeah.
Okay. That's what happens when you try to shave steps by skipping some algebra, especially in an audience. Because you even know what mistake I made, right? Like, looks like maybe I added instead of subtracting. Cool. So here's the next point. So here are two lines. Y equals 3x plus 4, and one given by y equals negative 2 thirds x plus 2. And, well, we can even label them. This one has positive slope. So which of these two lines should I highlight as red? Well, I haven't really given you a good way to answer the question. It should be the one with positive slope. If you look at those two lines, does it appear as though they meet at a right angle? They certainly seem to be perpendicular. There's also a relationship between these two slopes. Do you see any? How are those two slopes related?
Opposite, reciprocal.
Yeah, they're opposite with the sign, and they're reciprocals of each other. One of them is 1 over the other. Negative 2 thirds is the negative of the reciprocal of 3 halves. And in general, that's always true. Two lines are perpendicular if their slopes are negative reciprocals of each other. If n equals negative 1 over m. And let's just check that in a single example. Let's just use it to do a computation. Are these two perpendicular? Yeah, they are. Negative 1 over 3 halves is indeed negative 2 thirds. So this result does indeed claim that these lines are perpendicular to each other, which we saw they were in the picture. So let's do, well, maybe I'll give you guys an option here. So do you think if I told you a line were perpendicular to this line, 3 halves x plus 4, and passed through the point 1, 1, is that enough information to completely determine that line? Yeah. And maybe I'll even say just this much. What's the slope of the new line? So the new slope should be negative the reciprocal of this slope. Do you also know a point on the line? So you can write down an equation for the line, and it just says equation and not linear function. So y minus y1 is equal to m times x minus x1. Gives an equation for the line. You feel okay about that? Any questions before I move on to something maybe just a little bit more sophisticated? Good. So we've developed a fair amount on the theory of functions. We focused in towards linear functions a little bit. Now I would like to take a step back and walk slightly more abstractly, and let's just think about graphs of functions. Yeah. Yeah. Did I trump anyone else? extras. Okay, I'll grab them afterwards. If you want to bring them up, I'll grab them afterwards regardless. Sometimes I'm bad at counting / remembering how many people should be in a row. So let's just remember really quickly, the graph of a function is all points of the form x comma y with the y value being the function evaluated at the x value. Right? That's just generally true. If I give you an equation, its graph is all x, y values that satisfy the equation. Graph of a function is asking you to satisfy that equation. Here's an example. Here I claim is the graph of f of x equal to the square root of x. Let's make that arrow a little bit bigger. It goes on. By looking at that graph, does it appear as though the point 4, 2 is on the graph? Yeah. Looks like. Should it be? Hopefully, if it is. And you can check that it should be. Right? If the point 4, 2 is on the graph, well, that means that this x value should correspond to that y value. So you need to ask yourself, is 2 equal to the square root of 4? Is it? So this point should indeed be on the graph. Looking at the graph, is there any point on the graph with an x-coordinate of -1? Should there be? Why not?
It starts at 0, 0, and like you can't do a negative, it'd be an imaginary number.
Yeah, you can't put a negative into a square root and expect a real number solution. Yeah, that's absolutely right. So the answer to that, no. Should there be? No. If -1, y were on the graph, then you'd wind up with y equal to the square root of -1. But you can't have a negative in a square root. This number would not be real. There is no real square root to -1. In general, you can use a graph to do computations by doing exactly what you did right here. If you are given a graph, you can compute f of x for any fixed x value by using its graph. You can look over that x value and see what y value is on the graph. For example, do you think you could use that graph to approximate what the square root of 2 is? Yeah, I think so. If you wanted to compute the square root of 2, you would look at an x value of 2. You would go up and you would see what that y value is. What does it look like that y value is approximately? You can't be that precise. There's not enough information here to be that precise. Yeah, it's 1 and then maybe a third of the way up. So you take x equal to root 2 over that x value. Nope, x equal to 2. Over that x value, it looks like y is somewhere around 1.3. So it looks like the square root of 2 is something pretty close to 1.3. And that's the best you can do on this particular graph. That make sense? So let's do, if you like, a bad example, a non-example. So let's suppose I tell you that a function has the graph given to the right. By looking at that graph, what does it look like f of 1 should be? Let's follow through the instructions. So I'll go and I'll look at x equals 1. What y value do I see corresponding to that x value?
Plus or minus 1.
Yeah, 1. And I also see -1. So it looks like I see y equals 1 and y equals -1. So it looks like f of 1 should be 1 and -1. So is that a function? No, a function's only allowed to take an input to a single output. So is that graph actually the graph of a function? No, and there's a general thing at play here. The vertical line test tells you which graphs will actually be graphs of functions. If I give you a graph in the xy plane, then it's the graph of a function if each vertical line hits the graph at most once. That makes sense? Maybe said in a different way, each x value corresponds to, at most, one y value. And so let's just appeal to that vertical line test and ask some questions. Is that graph the graph of a function? No, there are lots of x values that correspond to multiple y values. In fact, I see some that seem to correspond to like at least 3 y values, which is bigger than 1. Is that the graph of a function? Yeah. You take any vertical line, yeah, all of those look like they cross the graph exactly once, and 1 is at most 1, so 1. Is this the graph of a function? There's some contrast. Folks for yes? Folks for no? Okay. So let's talk through it. So presumably, you're upset because there are some vertical lines that you can draw, like that one. There's a vertical line that does not cross the graph. So this vertical line crosses the graph in 0 points. That's why I added the line about it being at most 1. Is 0 at most 1? Yeah. At most somehow means less than or equal to. So this is still fine. It's still the graph of a function. I guess that x value won't be in the domain of the function. Zero is less than or equal to 1. This is still a function. That makes sense? Good. So maybe I'll give you an overview of what we're going to talk about from here. So we're studying graphs and what they can tell us about functions. Looking at a graph, we'll figure out how to read off the domain. Which, remember, the domain is like all valid inputs. So all inputs where you can make sense of the output. And we'll think about this using examples. We'll think about range and how to compute that from a graph. We'll do maybe one example where if you have a graph that models some behavior that you're interested in, you can use that graph to make predictions. And finally, the last thing we'll do is we introduce this idea of a piecewise function when we talk about absolute values. We can graph piecewise functions. We'll think that through, and that'll be the last thing we do today. So there's an overview. Hopefully getting the wide-scale picture of what today will be is useful. So here are some graphs. They're there. I claim one of them is y equals f of x. The other one is y equals g of x. Are both of those graphs of functions? Yes for both? No for at least one? Good. Yeah. You line these up. You start drawing some vertical lines. Some of them cross in 0 points, 1 point, 1 point, 1 point. Good. These vertical lines cross in 1 point, no points, and then 1 point. If these are actually functions, I should be able to plug in numbers and get numbers out. That's what functions do. So by looking at the graph of y equals f of x, what does it look like f of 0 is? Yeah. Take an x value of 0, you go up. Yeah, that looks like it's the point at y equals 1. What does it look like f of negative 1 is? 0. Right, the solid dot should tell you, just like when we're talking about intervals, a solid dot means that point is on the graph. How about f of 1? What does that look like it is? Be approximate if you must. Yeah. So one bit of shtick I like with these is I can zoom in really close. So if you're interested in x equals 1, so you start at 1, go up. Yeah, it looks like it's bigger than 1, less than 2. Maybe it's less than 1.5 even, but that's okay. That's precise enough for me. How about f of negative 2? Yeah, I see people just shaking their heads, so I guess the answer you're thinking is f of 2 is equal to no. Which probably isn't literally what you're thinking. Somehow just doesn't exist. You follow the instruction. You start at x equals 2 and you look above and below. Do you see any y values over that x value on that graph? Let's say that another way. So remember, the domain of a function is all inputs which result in valid outputs. So is negative 2 in the domain of this function? Negative 2 is not in the domain of f. Let's play the same game for g. What's g of 0? Doesn't exist. And maybe I'll advocate DNE, but does not exist as a reasonable abbreviation. Not that you have to use, but. How about g of negative 1? I hear some negative ones. Do I hear any other options? Yeah. Doesn't exist. Right, so the open circle, the fact that that's an open circle means that that point is not actually on the graph. Oh. So the open circle means that the point negative 1, negative 1 is not actually on the graph. The graph gets really, really, really close to the point negative 1, negative 1, but it never actually makes it. So I'll ask again, what's g of negative 1? It also fails to exist. How about g of 1? Is negative 1. The solid black dot tells you that 1, negative 1 is on the graph. And I guess, I was supposed to. So I like the idea of color coding, but I'm incapable of doing it consistently. All of that was supposed to be in red. G of negative 2. I think it does exist. So look at the graph. You'll look over an x value of negative 2. There's an x value at -2. Does that straight vertical line cross the graph? At something close to 1. So it looks like g of -2, oh, zoom back out, is approximately equal to 1. Nice. So notice, by doing something one point at a time, we managed to do something a little bit better than just evaluating the function. We also answered the question, does it even make sense to evaluate the function? We determined whether these inputs were even in the domain. Do you think you could do that in complete generality? If I gave you the graph of a function, can you read off the domain? Yeah, I think so. Let's do it for these examples, and I'll zoom in close again. And so let's just start going left to right. So these x values correspond to any y values? So are they in the domain? And it's going to change to being in the domain at some point. Tell me when that is. Okay, well, you guys are supposed to say right now. But at about there. So what x value is that? -1. So -1 suddenly is in the domain. And if I keep on going right from here, are all of these inputs in the domain? And I guess one question you can't answer is, does the graph just stop at x equal to 5, or does it keep on going? It's not clear from this picture. Maybe I will make it clearer by there. Now it's supposed to go on forever. So what's the domain of that function? -1 to infinity, including or excluding? Including. So the domain of f is, oh, you can't see that. Let's play the same game for g. There's more stuff that I've drawn on here to mess up the graph, but you might just have to forgive that. Cool. So, start at -5. Is that x value in the domain? Because I see a y value that it corresponds to. It looks like that y value is about, is it about 4 or about 5? I don't want to count. I think it's about 4. Plus, I don't care, right? You don't need to evaluate it to be able to say whether it's in the domain. You just need to be able to say, could I evaluate it? And you could. So all of these are in the domain, and it changes at some point. Changes. There-ish. What x value does it change on? Negative. -1. And -1 is not in the domain. So I see everything less than -1 all the way up to -1 exclusive. So it looks like part of the domain of the function g goes from -infinity to -1. Is that everything in the domain? No. When does the domain, well, I think that we get the idea without me doing more of the zooming in. Where do the inputs start being in the domain again? Including 1. And then all the way on to infinity, assuming that there were arrows on them. Which there might not be, right? Maybe instead I would have decorated the endpoint with solid dots, in which case we would have the domain like stops at x equals 5. People feel pretty okay about that? Nice. So you can read off the domain just by looking at a graph. Do you think you can also read off the range? And let's do this in a single example. So here's, again, the graph of a function. Is that actually the graph of a function? Yeah. Each x value corresponds to at most one y value. By looking at that graph, can you find an x value that results in f of x equals 2? Well, let's think about this. On the graph, f of x is the y value. So I'm looking for a y value of 2. This requires me to actually draw a straight line. Does that straight horizontal line at y equals 2 cross the graph of the function? Yeah. So now I just need to find the x value that that point corresponds to. So that looks like it's about there. So what x value does it look like according to this picture? What x value does it look like gives you a y value of 2? Yeah, 4. Your picture is probably better than mine. So it looks like x equals 4. 1, 2, 3, 4 gives f of x equals 2. Similarly, for what input x is f of x equal to negative 1? Well, let's go through the same motions. So I'm looking for a y value of negative 1. So let's draw a y value of negative 1. Does that line cross the graph? So is there any x value which corresponds to a y value of negative 1? Nice. So it looks like negative 1 isn't actually an output that is attained by the function f. So is that value negative 1 in the range? Who remembers what we said the range is defined to be? Let's just state that real quick. If I give you a function, the range of that function is all attained outputs. All outputs of the function that actually correspond to inputs. So it looks like negative 1 is not such an output. It's not actually hit by the function. So negative 1 is not in the range. So there are some takeaways here. The first is that if you want to solve the equation f of x is equal to c from a graph, what you need to do is draw a line at that y value. Find all x values of points where the graph crosses the line. There might be more than one, there might be 0, there might be just 1. Does that make sense? Say it again?
Is that a C or?
Yes.
Oh.
Yeah, the thing that looks like a tidal wave. Yeah, in order to keep my C's from looking like parentheses, I draw a cursive C. I'll try to follow that convention, and my cursive C's aren't terribly good, so they look like a tidal wave. But there's something generally true here, right? So if there are no x values that correspond to a y value, that means that y value isn't in the range. But if that y value is hit by some x value, then that y value is in the range. So if you want to know the range of a function, it's just all y values which actually appear on the graph. That makes sense? So let's answer some questions just using these particular graphs. So let's see, let me decorate. Let's put solid dots on the end of this one. Let's put arrows on the end of this one. Arrows everywhere on this one. Let's compute domains and ranges. So the function, well, I guess false questions first, is this actually the graph of a function? Good. What is the domain of that function? all the x values that you see on the graph? What x values do you see on that graph? -5 to -1. Including or excluding? Including, because of the solid dots. Is that everything? What's the rest of the domain? 1 to 5. Cool. What is the range of this function? You said, yeah, -1 to 4. Cool. Feb7Math? Next one. What does it look like the domain of this function is? The arrows are supposed to tell you that the function continues along that pattern forever wall.
Negative infinity to infinity.
Domain looks like it's -infinity to infinity. And infinities can never be included. They're not actually numbers. What does it look like the range of the function is? Would you want to include those numbers or exclude? I don't know. How many people would want to include? How many people would want to exclude? So, those of you who want to exclude are thinking, well, it looks like it's getting really, really, really close to 2, but I don't think it actually makes it to 2. Those of you who want to include are thinking, well, it looks like it makes it exactly to 2 and then is just constant at 2 forevermore. And you can't tell the difference from this graph. So whether you include or exclude based on this particular picture is impossible to tell. Now, how did I generate that graph? I used an explicit function, which I won't tell you what it is because it's not relevant for this exercise. I happen to know that it never actually attains those values. But if I want to give this question on like an exam, I would be happy either way because you can't tell. This next one, this picture of a semicircle. Well, what's enforced? Is it the graph of a function? Folks say yes. Anyone put up? Okay, good. Yeah, it is the graph of a function. What is its domain? -2 to 2, not including. Because those are the x values that you see. What y values do you see on this graph? Zero to 2. Including or excluding? Exclude 0, include 2? Because you check these y values, y value at 0, nope, there are 2 open circles there, so it doesn't actually get hit. 2, yeah, 2 is actually on that circle. People feel pretty okay? What if I want to change it just a little bit? And I know that this is unfair because I'm going to change the example now that you've already written down everything. What if I were to fill in just that circle? How would that change? How would that change the domain?
Include 2.
2 would be included. How would it change the range? Would now be included? Because there would be a single input which hits 0. And that's enough. The range doesn't care how many times 0 is hit. It just cares that it's at least once. And this last one, the graph of 1 over x. Yes, last time I didn't give you formulas, but I did this time. That is explicitly the function y equals 1 over x. What is its range? No, domain first. What is its domain? Like domain is like x of x values. Are these x values in the domain? Is that x value in the domain? No, it looks like it's shooting off to infinity or negative infinity on either side, but infinity is not actually a number, so 0 doesn't correspond to anything. So it looks like negative infinity to 0. I want to exclude 0. What about numbers bigger than 0? Are they in the domain? And the range is the same thing. Cool. Nice. So there's one takeaway. Totally in the abstract, if you have a graph, you can evaluate, you can solve equations, but you can also do something much more abstract than that. You can ask, does this input even make sense? Can I evaluate at this point? Can I find the domain? Can I solve an equation by looking at the graph? And the answer to whether or not there exists a solution to the equation is the answer to the question, is this thing in the range? So you can compute the range just by looking at the graph. The next thing that I want to do is going to wax back towards the applied illness. So here's a model. So a population of bacteria living in some environment. They can grow. Over small periods of time, populations tend to follow exponential behaviors. There's an exponential graph. So here's a model which you're told predicts how this population of bacteria will go. So by looking at this graph, what does it look like the population is and when you begin your experiment? At t equals 0. Yeah, so I guess it looks like it's 1, but the population is in millions. After 2 hours, so at time equals 2, what does it look like the population is close to? And I guess there are more than one way to write 2.5 million. 1 million happens to be 10 to the 6, so there's what's called scientific notation. There it is, just as a number expanded. When time is at 5, what does it look like the population is approximately?
10.
Again, scientific notation, that would just be 10 to the 7th. That makes sense? So once you have a graph that's supposed to model the behavior of something that you're interested in, you can make predictions by staring at that graph. And as any decent model, this model will only apply for short periods of time. At some point, there will be more bacteria than can possibly fit in the petri dish you're looking in, so this model can't continue walking forever. But you can make predictions until it does fail. So let's do one last type of example. Let's think about piecewise graphing. And I want to motivate it by the graph of the absolute value function, which is given by negative x when x is less than 0, 0 when x is equal to 0, and x when x is greater than 0. And let's try to generate the graph from Gauss principles. So many of you may already have a pretty good idea of what the graph is going to end up looking like. But I'm going to try to motivate graphs of piecewise functions by trying to generate this graph. And so I'll try to graph it by graphing each piece one at a time. What does the graph of y equals negative x look like? Well, it's a linear function, so its graph will be a straight line. What will be the slope of that line? Negative 1. What is a point that should be on that line? When x is 0, it looks like you get y equals 0. So that's enough. So there's, I'll graph each piece one at a time, and I'll try to obey some color coding conventions. So there's the graph of y equals negative x. This piece. What does the graph of y equals x look like? Well, it's a straight line. Slope is because it's y equals 1x. What is a point that it passes through? X equals 0, y equals 0, I guess? So now what I'll try to do is I'll go left to right, and for each point I'll try to decide whether I care about the green graph or the red graph. So, for negative values of x, do I care about the green graph or the red graph? The green one? Does anyone in the room have color issues? Okay. If you do and want to send me an email, then I can change the way I do these. So for all of these negative values, I care about this green dashed graph. So I'll go ahead and shade those in, because those are the points that are actually on the graph of the equation. It looks like something changes at x equals 0. At x equals 0, what y value do I get? 0? So it looks like this carries on. It stops applying at 0, but at the point 0, it continues to apply. When x is positive, do I care about red or green? Red. So for positive x values, I'll shade in the red piece. Aha! There's the graph of the absolute value function. It follows negative x for negative values of x. It goes through the point 0, 0. Then it switches to following positive x for positive values of x. That makes sense? Do you think we could do this for any function that I give you a piecewise description of? Yeah. Let's do this one. I think we have time for it. Let's try to sketch the graph of the function which is 0 when x is less than 0, which is 0 when x is bigger than 1, and which is 1 when x is between 0 and 1 increasing. So let's think about each piece one at a time. What does the graph of y equals 0 look like? Straight line at y equals 0. And green, apparently, I want to color that one. What does the graph of y equals 1 look like? Flat line at y equals 1. And now we'll play the same game. For each type of x value, I'll decide which one I care about. When x is less than 0, which piece do I care about? Green one. So that means I want to follow the green graph until I get to 0. Once I actually get to x equals 0, which piece do I care about? So, right at 0, this point is not on the graph. This point is instead. Then I'll start following red. How far do I continue following red? When does it change again? At 1. So something's going to happen at x equal to 1. At x equal to, well, should I draw a solid circle there or an open circle? Solid. Because when x is equal to 1, I still get y equals 1. And then I'll switch back to green. And that graph is totally unreadable, especially over the projector. It's not even great in person. You can't really tell the difference. So neato. So I guess it makes sense that it's a little bit behind where I want to be. So here's something that I'll encourage you guys to do. Figure out how to graph this piecewise function. And I'll even help you out by giving you the color coding right now. X squared minus 4 is this one. 4 minus x squared is this one. A highly similar problem appears on the homework. And I'll also do something at the very least which will be similar to a quiz in which I might ask you to graph exactly that function online. So feel free to come by my office hour, which is right off my class on Monday, and you can ask me about it. There might be some minor revisions that happen during the noon hour. That being said, if Monday rolls around and there are problems that are assigned and you don't know how to do this, you didn't do this example. Oh, wonderful. Thank you.